I'd like to now talk about correlation coefficients. Correlation coefficients are usually denoted by the Greek letter rho. Okay, so that is a Greek letter rho. It's not a funny P. It's the Greek letter rho. And the definition of a correlation coefficient is it's the covariance divided by the product of the standard deviations of the two variables. Now, if we insert the definition of covariance from above, and then we can bring these constants, so these are just constants inside of the expectation using a result we had last week, we can write this in a very special form. So we have x minus its mean divided by its standard deviation, and that ought to look familiar to you. That's a z-score. Okay, so that's something that's expressed in standard units. It has a mean of 0 and a standard deviation of 1. Then over here we have y minus its mean divided by its standard deviation, which is also a z-score. So what we're really doing with a correlation coefficient is just finding the average of the product of the z-scores. Now, I think this formula lends itself to a very simple interpretation. So let's go over to my sketchpad for a second, and I want to illustrate this. So let me just remind you. So the Greek letter rho, that's the way I make my rows, is just the expectation of x as a z-score times y as a z-score. So let me draw a scatter plot for us, and let's just say that my scatter plot looks something like this. Okay, so basically the mean of x is about 0. The mean of y is also about 0. So what I'd like you to note is that for all of these values out here, zx is going to be positive because they're all above average, and zy will all be positive because they're above average. Likewise, all these points down here have zx less than 0 and zy less than 0. So when I take the product of two negatives, so zx times zy down here will be positive usually because both of these values are negative. I take a negative times a negative, I get a positive. Likewise, zx times zy will usually be positive out in this region. So on the average, the product of these z-scores will be positive. So rho in this case will be very large because we're taking the product of a bunch of positives and then product of a bunch of negatives, which give us positives, and we end up with a positive correlation coefficient. Now, just for contrast, let's say my scatter plot looked something like this. All right, so again, this is my x-axis, this is my y-axis, and all of the z values out here, so zx's, will be positive for the most part. My zy's, these are all below average in this direction. So you take a zx times a zy, that is less than 0. What do we have up here? Well, up here, zx is less than 0, zy is greater than 0. The product is going to be less than 0. So if I average a bunch of stuff that's less than 0 with a bunch of stuff that's less than 0, my correlation coefficient will be less than 0. One more situation will be this one, where we have really no systematic pattern. So in this quadrant, both zx and zy are positive, so I'll just put plus plus. Over here we have negative plus, here we have minus minus, here we have the x's are positive, the y's are negative. So I have a bunch of positives here and I have a bunch of negatives here. Rho will be about 0 in that case since I'm averaging these z values. All right, so that's a very simple interpretation of a correlation coefficient. I hope that helps with your intuition of this. We could go compute the correlation coefficient for my little problem here. Now, we could do it one of two ways. We could do it with the definition. So just as I, computed my expectation of the centered variables to get the covariance, if I were to divide this by the standard deviation of x times the standard deviation of y, I would get the correlation coefficient. Or what I could do is use the formula that we just went through. Okay, so this is going to be the expectation of x times y minus e at x times e of y. So let's just go plug this in. And so what is the actually, that formula is wrong. Let me fix this up for us before I get too far. This is actually the covariance of x and y. Where is that coming from? Why don't we go check? This is where it's coming from. It's the covariance divided by the two standard deviations. So let me fix this up. This is going to be divided by the square root. Let's write it like this. Sigma x times sigma y. And so let's go compute that. So what is the covariance? It's 3.25. Then I need to divide it by the square root of the product of my variances. So here are my two variances. And so the answer is about 0.47. So let me interpret this. What this says is higher values of x are associated with higher values of y. Okay, so when x has a good day, y tends to have a good day also. All right, let's go back to the course packet. There's a few more results that you need to know about from basic probability theory. So when x and y are independent of one another, then e at xy is just the product of these expectations. Now, we've seen something like this before up here. So if e at xy is equal to the product of the expectations, this difference will be 0, and the covariance will therefore be 0. So an important result is whenever you have independent random variables, the covariance will be 0. All right, moving on, we have two more formulas that are very similar to the formulas we had before last week, where we were finding the expectation of a linear combination of a single random variable and the variance of a linear combination of a single random variable. What happens if you have two random variables? So this, I'm going to call this a linear combination of my two random variables. It turns out that you can just pull the coefficient out and also distribute the expected value sign. So I think we need an example of this. So maybe as the owner of this company, I'm really interested in the total amount that my two salespeople are going to sell today. So what is the total amount? Well, it's whatever x sells plus whatever y sells. So what is this, what is the expectation of t then? Well, the expectation of t is just going to be the expectation of x plus the expectation of y. So if we go back and look at our notes, the expectation of x is 0.95, and the expectation of y is 1.05, and I can do that in my head. Every day, I expect to sell 2 units between my 2 salespeople if I'm the manager. Now, another really important question is, how much uncertainty is there with this 2? So what is the typical amount that I would differ from this? In other words, what's the standard deviation or the variance of this? So we can go find the variance of t. Now, how do we find the variance of t? Variances, let's just go back to my course packet for a second. Variances are a little trickier because it's actually whatever constant there is before the x, we can pull that out, that gets squared. Whatever constant there is in front of y, that gets squared, plus 2 times both the constants times the covariance. So let's go find that number. So this would be the variance of, we can think of this as 1x plus 1y. And this is just equal to, well, 1 squared times the variance of x plus 1 squared times the variance of y plus, okay, 2 times 1 times 1 times the covariance between x and y. So let's go fill in the numbers here. The variance of x is 0.6475. The variance of y also happened to be 0.6475 in this example, plus 2 times the covariance. I didn't write down the covariance. We're going to need to go look that up. So the covariance is 0.3025, and that would give the variance of t. Now, I don't think I'm going to do this in this video, but if you don't believe me that my results are correct, you could define an h function and evaluate that h function for every possible combination of x and y, and then add the product of that h function with the probability values, and you should get exactly the same mean that we got, which was 2. You could do the same thing with the variance. In fact, I think that would be a very good exercise for you to try that, just to see if you get the same thing going straight to the definition instead of using these shortcut formulas. I have to say, these 2 shortcut formulas are perhaps 2 of the most important formulas we're going to have in this course. We're going to use them time and time again, so it's very important that you're comfortable with them. I want to mention one lemma. So the lemma is, whenever x and y are independent, so if I have 2 independent random variables, then I can just distribute this variance sign across the terms, and I don't have to worry about the covariance, because that covariance, remember, we determined was 0. So that's going to be a very useful result to us, because often we're going to have independent random variables. So the last thing that I want to say is that everything we just did, which I think is fairly easy to understand when you have 2 discrete random variables that only take a couple values, everything that we've just done can be repeated when you have 2 continuous random variables. It's just that you're going to have to use integrals rather than sums. And so it's there are many problems in Devore where he gives you some continuous distributions, and it would be good for you to try this, just all the things that we've done here. This is like everything you need to know about 2 random variables on one slide. It would be good to try that with a continuous distribution as well. Okay, so I would suggest that you go practice now. Practice some problems from Devore. Another thing that you might want to do is to see this in practice, so go watch my next video, which shows how we can estimate all these probabilities that were just handed to us and see our conditional distributions and so forth.